In an experiment, sometimes the outcomes of an event compared to another event are considered mutually exclusive or independent. Let's take a look at an example here. The experiment we're looking at is flipping two fair coins. First, we want to know what the sample space looks like. I suggest drawing out the sample space maybe by using a tree diagram. Our first coin has two choices. Either we have a heads or we have a tails. So this represents the first coin toss. When we go to toss the second coin, we have to consider that it's another branch of our tree diagram. So our second coin could also have an outcome of a heads or a tails. And that's true no matter what we got on our first toss. Reading down our tree diagram, I can see one possible outcome has heads first and heads second, so head, head. Or maybe we had heads first and tails second, or head, tail. We have four different possible outcomes of this experiment: head, 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 tail, tail, head, tail, tail. Our sample space then would look like the set S with the elements head, 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 tail, tail, head, tail, tail. Four different possible outcomes in our sample space. Let's take a look at some of the events that might happen in the experiment. Event A, the event of getting at most one tail. At most one tail suggests that we would not get two tails. So looking in our sample space, we could have 0 tail, 1 tail, 1 tail, or 2 tail. At most one tail would allow for 0 tail or 1 tail. There are 3 possible outcomes with those results out of the 4 total outcomes in this experiment. So we have a probability of 3/4, which is about 75%. What about the event of getting all tails? Well, we're only flipping 2 coins, and out of the outcomes, there's only one that has both coins on tails, so that would be 1 out of 4, or 25%. What about the event of getting all heads? Well, that's very similar to getting all tails, but it's the outcome head, head, and there's only one of them. So this would be 1 outcome of getting all heads. If we're asked to find the probability of B, event B, getting all tails and getting all heads, that would suggest one trial of the experiment where the result is both all heads and all tails. That's flipping 2 coins. Each coin has only one outcome at a time. It's not possible for the 2 coins to be both all heads and both all tails at the same time. So the probability of this happening would be 0. It's impossible. You can't have 2 coins that are both head, head, tail, tail. Not possible. Events B and C having a probability of 0 is an indicator that B and C are actually mutually exclusive events. They do not have any overlap. What about the event of getting more than one tail? More than one tail would suggest that you have 2 tails. The only outcome with 2 tails is the tail-tail outcome. There's one of those. This is just like event B. All tails, more than one tail. The event description is different, but technically we're describing the exact same outcome. Oh, this one's got a typo. Event of getting a head on the first flip. If we consider the outcome where we have a head on the first flip, we actually don't care about the second coin toss at all. We just care about the first coin toss landing on head. And then whatever the second coin is, we know the first one was already head. There's 2 possible outcomes out of 4 in the sample space, so we could look at that as 2 out of 4. Or we could say, I don't care what the second coin is, I only really care about this first coin toss. And in the first coin toss, there's 2 possible outcomes, and only one of those is head. So we could do that problem both ways and we'd get the same result.